In this lecture, we're going to discuss the notions of basis and dimension for vector spaces. We begin with the definition of a basis. So, definition. A linearly independent subset B which spans vector space V is called a basis of V. So here we see that the basis has two properties. First, it's linearly independent, and second property is that it must span the vector space. Let's give some examples. So, as the first example, let's consider the standard basis of Fn. So here, Fn is a vector space of column vectors with n components, and we consider set B of vectors e1, e2 up to en, where e1 is a column vector 1 and all other components are 0. E2 is has 1 in the second component, and so on, and En has a 1 in the last component, and everything else is 0. Now, we claim that this is a basis. So to show that this is a basis, we need to prove two things. So first, that B spans Fn. So what does it mean? This means that every vector from Fn is a linear combination of vectors from B. Now, so let's take an arbitrary vector, a1, a2, up to an. So we can write it in the following way. We can write it as a0, a1, 0, and all zeros, plus 0, a2, 0, and all zeros, plus 0, 0, 0, an. So if we add up all vectors in the right-hand side, then we get exactly the vector in the left-hand side. And then, in the first vector, we can pull out a1 as a common factor. So we get a1 times 1, 0, 0, 0, plus a2 times 0, 1, and all zeros, plus an times a vector that has 1 in the last component, and everything else is 0. So what we see here is that an arbitrary vector from Fn can be written as a linear combination of the given n vectors. So this means that this basis spans Fn. Now, the second property that we need to verify is that this set is linearly independent, right? So what does it mean? So this means that if we have a linear combination of these vectors that is equal to a 0 vector, then this would imply, and this is we need to check, that all the coefficients of this linear combination are equal to 0, right? But, so on the left, in the left-hand side, so this calculation tells us that the left-hand side is equal to the vector a1, a2, an. And the right-hand side here is a 0 vector. So it's 0, 0, 0. And of course, if we have equality that the vector a1, a2 up to an is equal to the vector 0, 0, and all 0, then of course this implies that all ans or all ak's are actually equal to 0. And we obtain exactly what we wanted. So we show that if a linear combination of these vectors is equal to a 0 vector, then all coefficients must be equal to 0. So here we proved that this set spans Fn and it's linearly independent. So this means that this is a basis of the space Fn. So this basis is called the standard basis of Fn. The standard basis is not the only basis in Fn. So typically there are many ways how one can choose a basis. And let's give another example. So let's take the following two vectors in R2. So let's take vectors 1, 1 and 1, minus 1. So we claim that this pair of vectors forms a basis of R2. Now, these vectors are not proportional. Right? So neither of them is a constant multiple of another. And so we know that for two vectors, this is the condition for linear independence. So this implies that this set, let's call it B, is linearly independent. And it is also possible to show that these two vectors span R2. So indeed, so let's take an arbitrary vector. And so we claim that this can be written as a plus b over 2 times 1, 1 plus a minus b over 2 times 1 minus 1. Right? So if we calculate the right-hand side, so then we can see that the result of the calculation of the right-hand side is exactly the left-hand side. And so the conclusion from here is that every vector in R2 is a linear combination of these two vectors, 1, 1 and 1, minus 1. And that exactly says that B spans R2. So the set of all linear combinations of these two vectors is the set of all vectors in R2. So this means that this set will satisfy both conditions. It's linearly independent and it spans R2. So this means that this is a basis of R2. For our next example, let's take as a vector space the space of 2 by 2 matrices over some field. So here we claim that an example of a basis here will be the following set of matrices. So we take 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So we take a set of these four matrices. So we claim that this is a basis. So to show this, we need to show that this set of four matrices spans the space of all matrices and that this set is linearly independent. Okay, so to show that it spans M22, right? So what we do is we take a matrix A, B, C, D and write it as a sum of four matrices. So it's A0, 0, 0 plus 0b 0 0 plus 0 0 c 0 plus 0 0 0 d. Right? So if we add 4 matrices on the left, then we get exactly 4 matrices on the right, then we get exactly the matrix on the left. But then this is A times the matrix 1 0 0 0 plus B times the matrix 0 1 0 0 plus C times 0 0 1 0 plus D times 0 0 0 1. And now we just interpret this equality as saying that this matrix is a linear combination of the 4 matrices here. And what we see is that an arbitrary matrix from M to 2 can be written as a linear combination of the 4 given matrices. So then the conclusion is that, so the conclusion from here is that this set B, right, so this set B spans M to 2. And so the second property that we need is we need to show that B is linearly independent. And that would mean the following, that if we have a linear combination of this set of vectors, which is equal to a 0 vector. So if we have a linear combination which is equal to a 0 vector, but a 0 vector is a 0 matrix here, then this, we need to show that this implies that all coefficients of this linear combination are equal to 0. So this is exactly what linear independence means. So if a linear combination is equal to a 0 vector, then this linear combination is trivial. So this means that all coefficients are equal to 0. But the left-hand side we already calculated. So the left-hand side is simply the matrix A, B, C, D. And so now we are given that the matrix A, B, C, D is equal to the matrix 0, 0, 0, 0. But then this will imply that, of course, A must be 0, B must be 0, C must be 0, and D must be 0. Because this is the only way how these two matrices may be equal. And this is exactly the statement of linear independence. So we proved that if this linear combination is 0, then all coefficients of these linear combinations are 0 scalars. So our next example will be the space of polynomials. And here, so we're going to show that as a basis, we can take an infinite set. We can take set 1, x, x squared, x cubed, and so on. Right? So these are vectors in the space. So because in the space, vectors are polynomials, and we just select this sequence of polynomials. Now, so what we need to show is, so we need to show that this set B spans R of x. So this means that any polynomial is a linear combination of these, and 2, that B is linearly independent. Right, so we start with 1, and we take a polynomial, so f, which is a0 plus a1x plus a2x squared plus an x to the power n. Well, any polynomial can be written in this form. But then this is interpreted in the following way. It's a0 times 1 plus a1 times x plus a2 times x squared plus an times xn, x to the n. And so the way how we can interpret now this polynomial is that this is a linear combination of vectors from B. So now what we showed is that an arbitrary polynomial is a linear combination of vectors from B. And this means that the set B spans the space of polynomials. So the set of all linear combinations from B will give us all polynomials in R of x. And for linear independence, so we need to show the following, that if we have a linear combination, and here a linear combination is a finite linear combination of vectors from this set is equal to 0, then this follows that all coefficients are equal to 0. So now, if we have a0 times 1 plus a1 times x plus an times x to the power n is equal to 0, then, well, this means that this is a zero polynomial. And by definition, a zero polynomial is a polynomial with all coefficients being 0. So, of course, from here, it follows that a0, a1, and all coefficients that appear here are all equal to 0. And so this tells us that the set B is linearly independent. So if we equate any linear combination, any finite linear combination of elements from B to 0, then we can see that all coefficients of these linear combinations are in fact equal to 0. So this is an example of a vector space with an infinite basis. In our last lecture, we showed that any 5 vectors in F3 are linearly dependent. Or more generally, so if we take Fn, and in Fn we take k vectors, where k is greater than n, then the set of k vectors will be linearly dependent. So now we want to generalize this statement for vector spaces, which are not necessarily Fn's. And so here we have a theorem. So suppose vector space V is spanned by the set of vectors V1 through Vn. Then any set of k vectors W1 through Wk with k greater than n is linearly dependent. So proof. So to show that something is linearly dependent, we need to show that there exists a non-trivial linear combination of these vectors which is equal to a 0 vector. So we need to show that there exists C1 through Ck in F, not all 0, such that C1 W1 plus Ck Wk is equal to a 0 vector. Now, so what we are given here is that our vector space V is spanned by these n vectors. So this means that so vectors W1 through Wk are spanned by vectors v1 through vn. So what does it mean? This means that w1 can be written as a11 times v1 plus a12 times v2 plus a1n times vn. Then, so w2 can be written as a21 v1 plus a22 v2 plus a2n vn. And lastly, wk can be written as ak1 v1 plus ak2 v2 plus akn vn. Now, let us take these equalities and substitute them into the left-hand side of the equality where linear combination is equal to 0. So what are we going to get? So we're going to get the following. So we get that C1 times W1. So this will be A11 V1 plus A1n Vn plus dot 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 Ck times AK1 V1 plus akn vn. Now, if we rewrite this, let's group terms with v1, v2, and vn. So what's the coefficient at v1? So here we're going to get a11 c1 plus a21 c2 plus ak1 ck, and all of this times v1 plus, so what we will have times v2, so we will have a12 c1 plus a22 c2 plus ak2 ck times v2, and so on, plus a1n c1 plus a2n c2 plus akn ck times vn. And so this is this linear combination on the left, and we want to equate this to a zero vector. So how can we obtain a solution for this vector equation? So one way of getting this solution is to equate each coefficient to 0. So let's do that. So now we form a system of linear equations by equating each of the coefficients at v1, v2, and vn to 0. And we call this system with 2 stars. And what we say that every solution of this system of star star is a solution of this vector equation here, right? So because if all of these are equal to 0, then all coefficients on the left are also 0, and immediately we get that the left-hand side is equal to 0, and we get that this equality holds. So when we say solution, then of course the unknowns here are C1, C2, and Ck. But, so let us see how many equations here and how many unknowns do we have here. So here we have n equations and k unknowns. And k is greater or equal to n. So we have more unknowns than equations. So in our previous lecture, so let's recall, we proved the following fact, that if we have a homogeneous system, x is equal to 0, has more unknowns than equations, then it has a non-zero solution. So where the solution vector is not equal to 0. And that's exactly the case here. So here all a coefficients are fixed from decomposing w vectors in terms of linear combinations of these, and the unknowns are ci's. And here we have more unknowns than equations. So this tells us that this system of linear equations star has a non-zero solution where, so this C1 through CK are not all 0. And so that tells us that there exists a non-trivial linear combination star of W1 through WK, which is equals 0 vector. And this exactly tells us that the set of W's is linearly dependent. And that is exactly the claim of this theorem, right? So that the set W1 through WK is linearly dependent. So now, so what we obtained is that if a vector space is spanned by n vectors, then any set of k vectors with k greater than n is linearly dependent. Now, if we look at the special case of the space of Fn, then we saw that we have a standard basis here of n vectors. So this means that this vector space is spanned by n vectors. And so applying this theorem for the space Fn, we recover the result that we obtained last time, that any k vectors in Fn is linearly dependent provided that k is greater than n. And now, so this is a generalization of this theorem. So now it's we're not only talking about vector space Fn, but any vector space whatsoever. So let's give the following definition. A vector space V is called finite-dimensional if it is spanned by a finite set of vectors. So if a vector space cannot be spanned by a finite set of vectors, so otherwise it is called infinite dimensional. So, examples. So here, if we take Fn, or if we take the space of matrices, so M by N matrices over field F, so these are finite dimensional. Vector spaces. And if we take polynomials with coefficients in F, or we take, say, F, the space of functions on a real line with real values. So these are infinite dimensional vector spaces. Now, let us state the main theorem of today's lecture. So, theorem, so it has two parts. So, A, every finite dimensional vector space has a finite basis. So this means that in every finite dimensional vector space, we can choose a finite basis. And B, every basis of a finite dimensional vector space V over a field F has the same number of vectors. So this number is called the dimension of V. So for example, dimension of R2 is equal to 2. So what we see is that there is more than one way of choosing a basis on a plane. But every basis we choose will have two vectors. So this is the claim of part B. So that every basis will have the same number of vectors. And we know that R2 has some basis where we have two vectors. So this means every basis of R2 has two vectors. And this number 2 is called the dimension of the vector space. In order to prove this theorem, we need to obtain first a couple of auxiliary results. And so this is where we're going to begin. So we'll prove a couple of lemmas that will help us with the proving this theorem. And so we'll come to the proof of this theorem a little later today. Let us mention a couple of conventions regarding the empty set. So first convention is that we will assume that empty set is linearly independent. And the second convention about the empty set will be that the span of an empty set of vectors will be assumed to be a subspace that consists of a zero vector. Let us prove the following lemma. suppose vector u belongs to the span of vectors v1 to vk. Then the span of vectors v1 through vk together with u is equal to the span of the original set of vectors v1 through vk. Now, so in other words, if u already is in the span of these k vectors, then adding u to the set will not change the span. Another way of looking at this lemma is the following, that if u belongs to the span of v1 to vk, then we can remove u from the span of the larger set, and the span will not change. So let us give the proof of the lemma. So what does it mean that u belongs to the span of v1 through vk? So this implies that there exist scalars c1 through ck such that u can be written as c1 v1 plus ck vk. So this is what it means for a vector to belong to the span of other vectors. So now, we need to show equality of two sets. So to show equality of two sets, so we need to show that one, the span of the smaller set is a subset of the span of a bigger set, and two, that the span of a bigger set is a subset of the span of the smaller set. Right. So this is how we prove equalities of two sets. So to show that a set A is equal to the set B, we need to show that A is a subset of B and B is a subset of A. So the first property is fairly obvious. So let W belong to the span of V1 through Vk. So this implies that W can be written as a linear combination of these vectors. So it's A1 V1 plus AK Vk for some A1 through AK in F. But then this tells us that we can also write W as A1 V1 plus AK Vk plus 0 times U. And now this becomes a linear combination of this larger set. And so this tells us that W belongs to the span of V1 through Vk together with U. And here we proved that every vector from span of V's belongs to the span of V's together with U. So this tells us that we have inclusion here. So now, the more interesting part is the second part, right? So here, now we suppose W belongs to the span of V1 through Vk together with U. So what does it mean? So this means that there exist scalars B1 up to Bk and Bk plus 1 such that W is equal to B1 V1 plus bk vk plus bk plus 1 times u. But, so we recall that u has this expansion. So let's substitute this. So this tells us that w is equal to b1 v1 plus bk vk plus bk plus 1 times c1 v1 plus ck vk. So here we substituted the expansion of u as a linear combination of vk's. And now this can be written as b1 plus bk plus 1 c1 times v1 plus bk plus bk plus 1 times ck times vk. And this tells us that w, in fact, belongs to the span of v1 through vk. And here we show that any vector that belongs to the span of vi's together with u actually belongs to just the span of vk. And here this proves the second inclusion, right? And so we prove that we have inclusion of these two sets into each other. So this means that we have precisely equality, right? And so we prove that if u belongs to the span of v1 to vk, then we can either add u to v1 to vk, or we can remove u from this set, and the span wouldn't change. Now let us consider the following proposition. Every finite set of vectors S is v1 through vk has a linearly independent subset R such that span of S is equal to span of R. So basically, so the original set that we begin with may not be linearly independent, right? So we could start with some set which is linearly dependent. And here what we're claiming is that inside this set there is a smaller linearly independent subset which has exactly the same span as the original set. So this means that we can shrink the number of vectors in a set by obtaining linear independence, but keeping the size of the span intact. Now let's do the proof of this proposition. So if S is linearly independent, there is nothing to prove. So this means as R, we can choose the set S itself. Suppose that this first assumption is not the case. Suppose S is linearly dependent. Then what we proved earlier in the lecture on linear independence, that one of the vectors in S may be expressed as a linear combination of the others. So this means that some vector Vj is a linear combination C1 V1 plus Cj minus 1 Vj minus 1 plus Cj plus 1 Vj plus 1 plus Ck Vk. But then what this means, so this means exactly that Vj belongs to the span of the remaining vectors. So V1 to Vj minus 1, then we skip Vj, and we go to Vn. And then, by our earlier lemma, so if Vj belongs to this span, so this tells us that the span of this smaller set is equal to the span of the original set S, right? So this means that we can take the span of our set S, throw out Vj, and we obtain a smaller set that has the same span. And so then we iterate this process. So iterate this process, removing vectors so whenever the set is linearly dependent, and keeping the span unchanged. Right, so here, so what we did is we have thrown out one vector, but the span of the smaller set is the same as the span of the previous set. And so now, if this set of vectors is linearly independent, then we say that R is this set of vectors. If this set of vectors is linearly dependent, then there is one vector in this set that we can throw out and not change the span. So the span of the smaller set will be equal to the span of this set, or also equal to the span of the original set. And since we have only a finite number of vectors, so this process will terminate. With some set R. And so this process can only terminate when we get a linearly independent set. So this means that R is linearly independent. And at every step, we preserve the span. So this means that the span of R will be equal to the span of S. And so this is the claim of our proposition. So that in any set of vectors, we can find a subset which is linearly independent, but the span of the subset is equal to the span of the whole set. And we do it by throwing out vectors one by one and stopping when the set is linearly independent. So now we have all the tools to prove our theorem. So let's start with the first part. Every finite-dimensional vector space V over a field F has a finite basis. So proof. So what was our definition that the vector space is finite dimensional? So a vector space is finite dimensional, is called finite dimensional if it's spanned by a finite set of vectors. So there exist some vectors v1 through vk in V such that V is equal to the span of this set v1 through vk. Right? And let us set S to be the set of vectors. And by previous proposition, so this set S, so S has a linearly independent subset R, such that the span of R is equal to the span of S. But the span of S, by definition, is V. But then R is a basis of V. Indeed. So what's a basis? A basis is a set of vectors that has two properties. Its span is the whole space, and it's linearly independent. And the set R possesses both of these properties, so it is a basis of V. And of course, R is a finite set because it's a subset of a finite set. And so now we proved the first part of the theorem that every finite dimensional vector space has a finite basis. Now let us look at the second part of this theorem. Every basis of V has the same number of vectors. So for proof, so let us take two different bases. So let V1 through Vn and W1 through Wk be two bases of V. So then what do we know? So a basis is a set that is linearly independent and spans the space. So in particular, here we will know that the first set, V1 through Vn, spans V, and the second set, W1 through Wk, is linearly independent. Now, we proved the theorem that says that if we have a set of n vectors that spans a vector space, and if we take more vectors than n, then that would be linearly dependent. But here, the set W1 through Wk is linearly independent. So this tells us that k cannot exceed n. So k is less or equal to n. Right? So because if k were greater than n, then automatically this set would be linearly dependent. But now we twist this argument. Now we say that the set W1 through Wk spans V, and the set V1 through Vn is linearly independent. And using the same argument, we get now that n is less or equal to k. Right? So because now this space V is spanned by k vectors, and we have n linearly independent vectors in it. So this means that this n cannot exceed k. And these two together will imply that k is equal to n. And this means that if we have two bases of the same space, finite dimensional vector space, then the number of vectors must be the same. And so this common number of vectors in all bases of a vector space, so this is called the dimension. So this common number is dimension of V, right? So it's enough to have one basis in a finite dimensional vector space to know its dimension. So the dimension of a vector space is the number of vectors in its basis, and it doesn't matter which basis we choose. So now let us look at some examples of dimension. All right, so if we take the vector space Fn, then its dimension is equal to n, because here we have a standard basis E1 through En. So we constructed this standard basis in the vector space Fn, and because this basis has n vectors, our theorem says that any other basis of this space will have n vectors. So dimension of Fn is equal to n. Now, if we take the space of 2 by 2 matrices, so what we can say is that this space has dimension 4, right? So because we had a basis in this space that we wrote down. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Right? So we showed that these four matrices form a basis of the space of 2 by 2 matrices, and there are 4 matrices in this basis. So this means that the space has dimension 4. And maybe a question, so what's the dimension of the space of M by N matrices? Now, as a next example, let's consider V to be the space of quadratic polynomials. So it's all polynomials of the form ax squared plus bx plus c. Right? So where a, b, and c, they are real numbers. So we want to ask the question, what's the dimension of this space? And to compute the dimension of this space, so we need to construct a basis. And here we say that the basis of this space is 1, x, and x squared. Because what we have written here is just linear combinations of these 3 vectors. So this is a times x squared plus b times x plus c times 1. And so these are linearly independent, and they span the space V. And there are 3 vectors in this basis. So we say that the space of quadratic polynomials has dimension 3. So let us prove one more lemma about spans and linearly independent sets. So lemma, suppose the set V1 through Vk is linearly independent. And also assume that vector u does not belong to the span of V1 through Vk. Then the larger set V1 through Vk together with u is linearly independent. So let's prove this lemma. Proof. We will prove this lemma by contradiction. So this means that we're going to assume the opposite to what we need to prove. And then we will show that this assumption will lead to a contradiction. So this means that assuming the opposite of our conclusion is not possible. So we assume that the set V1 VKU is linearly dependent. So what does it mean? So this means that there exist scalars C1, CK, CK plus 1, not all 0, such that C1 V1 plus CK VK plus CK plus 1 U is equal to 0. So this is the definition of linear dependence. Now, consider two cases. So the first case, when CK plus 1 is not equal to 0. And the second case is CK plus 1 is equal to 0. So if CK plus 1 is non-zero, then this tells us that we can express CK plus 1 U as negative of C1 V1 negative CK VK. And then we can, if this scale is non-zero, we can multiply by its inverse. So U is equal to negative CK plus 1 inverse times C1 V1 minus CK plus 1 inverse CK VK. And then this tells us that U belongs to the span of V1 to VK. And that's a contradiction, because our assumption is that U does not belong to this span. Now, let's consider the second case, if CK plus 1 is equal to 0. If CK plus 1 is equal to 0, then in this equality we can drop the last term. So then this tells us that C1 V1 plus CK VK is equal to 0. And not all constants C1 through CK are 0. Right? So because here we assume that not all of these constants are 0. But CK plus 1 is 0, so this means that there exists a non-zero constant among C1 to CK. But then this says that the set V1 to VK is linearly dependent. And that's again a contradiction, because our assumption here is that this set is linearly independent. So this is a contradiction. And we see that in both possible cases, we run into a contradiction. And the source of this contradiction is our assumption that this set is linearly dependent. So this assumption is not possible, and so we conclude, so by contradiction, that this larger set V1 VK together with U is a linearly independent set. In our main theorem that we discussed today, we proved that any finite dimensional vector space has a basis and dimension. But if we take now a subspace in a finite dimensional vector space, it's a vector space itself. And so now we can talk about the basis of a subspace and the dimension of a subspace. And so in order to understand the relationship between the basis of a subspace and the basis of a space and the relationship between their dimensions, so let us prove the following theorem. So let U be a subspace in a finite-dimensional vector space V. Then any basis S of U may be extended to a basis B of V. And extended means that S will be a subset of B. So if we have a basis of a subspace, then we can enlarge it and obtain a basis of the whole space. So this is what this theorem says. So the proof of this theorem is reminiscent of the proof of our theorem about existence of a basis. When we proved the existence of a basis, we started with a spanning set, and we were removing vectors one by one until we reached linear independence. Now, in this case, we will do the opposite. So we will start with a basis of a subspace, and we'll start adding vectors one by one until we reach the spanning property. So let's give a proof. So consider the set S. So if S spans U, then there is nothing to prove. So we take B equals S. All right. So we know that S is linearly independent because it's a basis of U. If it spans the whole space V, then it will span V and be linearly independent, so it's a basis of V. Now, if S does not span V, there exists a vector U in V such that U does not belong to the span of S, right? So if span of S is not V, then there will be some vector which is in V but not in the span of S. And then we use our lemma, right? So our lemma says that if we have a linearly independent set and U does not belong to its span, then adding this vector will still give us a linearly independent set. So this will tell us, so by lemma, so S together with this vector U is linearly independent. And then we iterate this process. So if this set spans V, then we stop, right? So then we get linearly independent set that spans V. If it does not span V, then we can find a vector outside of this span in V, which, will be outside of this span, and then we add this vector to our set, and the resulting set is linearly independent by lemma. And we iterate this process, increasing this set, adding vectors one by keeping linear independence property. And so this process will terminate because any set containing more than dimension of V vectors is linearly dependent, right? So we know that once we exceed the dimension of our vector space, the set of vectors will be linearly dependent. And so this means that this process will terminate, and the way how it can terminate is only when we reach the span of V, right? So this one of these larger sets will be linearly independent and will be equal to this, and its span will be equal to V. And so this means that there is a larger set, because we started with some set S, which was a basis of a subspace, and we proved that there is an enlargement of this set, which is linearly independent and spans the whole space V. And so the set at termination, so the terminal set, is a basis of V which contains S. And as a corollary of this theorem, we get that if U is a subspace in V, so this tells us that dimension of U is less or equal to dimension of V, right? So this means that dimension of a subspace cannot exceed the dimension of a space. Well, this actually follows from our theorem that it says that if a space is spanned by n vectors, then any k vectors where k is greater than n is linearly dependent. So this also follows from that result. Our definition of a basis has two properties. A basis is linearly independent and it spans the whole vector space. So if we follow the definition, then we need to verify these two properties. And so the next theorem tells us that if we also know the dimension, then we can cut the amount of work in half. So theorem suppose dimension of a vector space is equal to n. So A, every set, every linearly independent set V1, Vn of n vectors in V is a basis of V, right? So here we only know that this set is linearly independent and it has the right number of vectors. So the number of vectors here is equal to dimension of V. Then we already can conclude that it's a basis. And B, every set of n vectors V1, through Vn that spans V, is a basis of V. So here we didn't know at the beginning whether this set is linearly independent, but we knew that it spans V, and it has the right number of vectors. So the number of vectors is equal to the dimension. Then, so the claim here is that we have a basis. So the conclusion here is that if we have the right number of vectors, so this means that the number of vectors is equal to the dimension of a vector space, which we know, then it is enough to check either linear independency or the spanning property. So this would be enough to conclude that we have a basis. So let's give a proof. So we start with part A. And again, we're going to use the method by contradiction. So by contradiction, assume that the set V1, Vn is not a basis. Well, a basis is something that's linearly independent and spans V. But if it's not a basis, then it's either linear independence fails or the spanning property fails. But here we know that linear independence property holds. So this implies that the span of this set of vectors is not equal to V. And so this means that it's smaller than V. Well, because everything happens in V, it cannot be greater than V. It can only be smaller. And so then this tells us there exists a vector u in V such that u does not belong to the span of V1 through Vn. But then we had a lemma. So by lemma, we had a lemma that if we have a linearly independent set and u does not belong to the span, then this larger set, V1 through Vn together with u, is linearly independent. But by theorem, so we proved that if we have more vectors than the number of vectors in a spanning set, then this larger set will be linearly dependent, right? And so here we know that dimension of our vector space is n. So it has a basis with n vectors. So this means that V is spanned by n vectors. And in this case, any set of n plus 1 vectors in V is linearly dependent. Right? So because V is spanned by n vectors. And so here we get a contradiction. On one hand, we know that any n plus 1 vectors in V is a linearly dependent set. And on the other hand, we conclude that here we have a set of n plus 1 vectors which is linearly independent. And the source of this contradiction was this assumption that the span of these n vectors is not V. So this means that this assumption is not possible. And so this tells us that this set, in addition to being linearly independent, also is a spanning set. And hence it is a basis. Now, let us prove part B. So we know, or we're given, that the span of V1 through Vn is the whole space V. Right? So, and then we proved, so we had a proposition that says that any set contains a linearly independent subset with the same span. So by proposition, there exists a subset R inside the set of V1 through Vn such that R is linearly independent and the span of R is equal to the span of V1 through Vn, which is V. So, but then this implies that R is a basis of V, right? So, because this subset R is linearly independent and it spans the whole space. But we prove that every basis of V contains the same number of vectors. So this tells us that R has n vectors, right? And so what did we get here? So we had a set of n vectors, and we have chosen a subset of n vectors. And so this tells us that R is equal to V1 Vn. And this shows that this is linearly independent, and so is a basis. And this completes the proof of this theorem. So here we prove that every set of n vectors that spans V is a basis of V.